with over 20 years of experience in the synthesis of aerosols, and with the help of a young and passionate team of scientists and engineers, VSP is unlocking a whole new world of possibilities at the nanoscale. We develop and commercialize a completely new technology to automate the production of new materials, and we are key nanotechnology providers in different industries such as catalysis, semicon, and health. Since 2014, we have helped scientists and industry leaders around the world to drastically reduce the development time of new materials by enabling the production of nanostructured materials for fundamental and applied research based on a simple to operate and scalable principle. And in this image, you have the current layout of our portfolio. There are many ways in which you can get in contact with us and request more information. If you would like to know more about VS Particle solutions and how they can help you up in speeding up your research, please check our application notes at vsparticle.com/applications. Or if you are interested in trying VS Particle technology in the safety of your own lab, you can do so by requesting a demo form via a form available at vsparticle.com or through email demo@vsparticle.com. Or for any other information regarding our technology, you can always contact our sales team. That was it from me. I will now give the floor to our presenter today to listen to the topic, and I will talk to you at the end of the session when I will take your questions and Joost will proceed to answer them. Thank you, everyone, and I'll see you in a bit. Enjoy.
Good morning, everyone. Let me get the presentation. Was everything working as it should?
Yes, everything is visible.
Wonderful. So, thank you all for joining, for watching this webinar. So, I'll start with a little bit about me. I have a background in chemical engineering, where I followed the Master of Science here at TU Delft. And during that time, I got into internship at VS Particle and a thesis with Professor Schmid-Ott, who was one of the co-founders of the company, where I worked on finding markets for VS Particle and developing a die attach process for attaching your chips to different substrates. During that thesis project, I collaborated with the ECTM group with some students of Professor Zhang. And after that, I applied for a PhD position in his group to work on similar topics. And at that point, we installed the VS particle generator in the clean room of our group. So as mentioned, I'm part of the Electronic Components Technology and Materials group, which is located at the Faculty of EMCS, the Department of Microelectronics. And we work primarily in the clean rooms of the ELSA COI lab. Now, this means that we make and develop new processes for microelectronics fabrication, so chips essentially, focusing on new materials and new system integration and reliability of electronics. So typical topics are MEMS devices, such as sensors and organs on a chip devices, but also packaging of electronics. So how do you make it more reliable, innovative ways to package your electronics, and flexible and stretchable electronics is a newer topic in our group. So to develop these new microelectronic materials, we also focus on nanomaterials, particularly in our group, graphene, of course, carbon nanotubes and nanoparticles, which is my specialty. And we've already developed gas sensors, temperature sensors, pressure sensors, also die attach materials. So imagine gluing a chip to another chip or to a PCB, and for MEMS devices. So back to the topic. If you want to connect your chip to the outside world, you have to somehow make a connection to your PCB to other chips or to the devices below it. Now, the most common way to do this is wire bonding. It's where you draw a wire from the chip to the surrounding electronics, and it has been the main way to do this since the dawn of the microelectronic fabrication. So it's widely established, and these days it's quite fast and highly reliable. There are some limitations. Primarily, you need temperature or pressure, or a lot of force at the very least, to create a reliable bond at the bond pad, because you need to melt and pressurize the metal to make it really stick to that surface. This is fine for most silicon electronics and other hard materials, but what if you want to, for example, connect to a polymer, to paper, or some fragile structure like membranes? You cannot use this pressure or even heat to create a strong bond, and wire bonding will thus be either very difficult or fail quickly. So alternatives are needed, and people have been looking into that for quite some time. Here are a few examples. So people have been trying to do lithography with electroplating to create well-defined lines over this step. So basically, you go on the side of the chip to create this connection. This works, but requires several processing steps and a lot of chemistry to get this right. So it's not as easy or elegant as wire bonding. So people looked into inkjet printing, which is quite fast and can create the type of connection that people need, but is limited to primarily flat substrates because you are basically working as a regular inkjet printing. So an extension of that is aerosol jet printing, where instead of using conventional 2D printing technology, it's more like a 3D printer that uses ink. And this is already closer to what a wire bond can do, right? You can now get a high step size. You can make the electrical connection to pads further away, and slightly more versatile technology. But you still have the downside that you need an ink. And ink formulation is challenging. There's a limited shelf life of it. You have a problem that you also have always a curing process. So you will need to heat the sample, or at least let it dry and rest for a while before you get a reliable connection. Even then, you'll have organic pollutants in your line, which will probably reduce performance. So the technology that we are using here, the method we're developing, is very similar to aerosol jet printing without the ink. So in a nutshell, it works like this. We use a fierce particle spark ablation generator to create an aerosol of gold nanoparticles, and we use a prototype of a fierce particle nanomaterial printer to shoot these particles at the substrate and print them. Now, if you do that on a chip, you can connect on the sides as well, right? You can just aim this jet at the edge of the chip and create an electrical connection. Benefit of this is that we no longer need any chemistry. So our lines are very pure and clean. So there's also no need for any processing afterwards. The lines will work as is. It also means you have no storage of any materials. There's no ink storage or shelf life. There is no intermediate process. You make the particles and you deposit them immediately, which also makes the process quite a bit simpler. The last benefit is that you can use it on a lot of materials because there is no temperature, high force, or wet chemistry involved. So the only limitation is that it has to survive the jet itself. I will not go into detail about the spark ablation technology because I assume many of you are already familiar with it, and it's also not the key innovation of this work here. But I will explain a little bit more about the impaction printing because that's the main technology that we're using. So as I mentioned before, we have a prototype setup of VS Particle inside our clean room that you can see here. And we use it to try to find innovative ways to apply these nanofilms in microelectronics. So the working principle is that you have a vacuum chamber with the nozzle, and the nozzle is connected to your sparked ablation generator. And the aerosol is accelerated through this nozzle because of that pressure difference. Now this jet can go supersonic speeds, and if you place it close enough to a substrate, so that's less than, I would say, a few millimeters, the inertia of the nanoparticles will cause them to land on the surface and stay there. So you're essentially spraying the aerosol on a substrate, and if you move the nozzle very close, you can even have, to a limited extent, some sintering. So the particles will be electrically connected. Now, this last property is very useful if you want to print conducting lines, and is one of the reasons why you can use these lines immediately after printing. There's no curing or heating or anything other needed. The other benefit is that because it only is a 1 millibar vacuum, it's compatible with most materials that I've tried. So we've tried to print gold on glass. We have printed on microelectronic epoxy packaging. See if you can add, do some additive manufacturing top of that package. For example, print an antenna would be one fun application, or connect entirely different devices on it. We've also printed on paper, which works very simply. So how do we now make this connection on the side of a chip? To do this, we fabricated dummy samples of silicon on silicon to prove that this process can work. This is the simplest possible device that we can make. It's just gold lines with placed on silicon. So we've glued a 10 by 10 millimeter silicon die on a larger one to create this step, and we use the excess of adhesive to fill the gap between the two substrates. This way we have a continuous transition from the top to the bottom. And we have these gold electrodes, so we can also probe this fairly easily with our electronic probe station and measure the electrical performance. Proof that we can also do this on more fragile materials, which is one of the key benefits of this technology. We also put these chips on paper, so we can still probe them, but we can also prove that the connection to the paper can be made reliably and that the performance is good enough. Now, this was always taped to a silicon carrier to make sure that the sample is easy to handle and mount, because paper is still fragile by itself. But if you remove this, the sample will still be functional. So then we printed them at an angle so that we can get the nozzle to reach the side and the top surface. And we placed the nozzle as close as we possibly could, but due to geometric constraints, that was usually 1/2 to 2 millimeters. And the resulting line that you see printed here in the bottom right, this is a top view, is slightly wider than the electrodes that we printed, which is not at all an issue as long as you don't short your electrodes. So what does the product look like then? For silicon, it's pretty much as you would expect. You have a gold line running from the, I'm gonna get my pointer, from the top to the bottom, following the sides quite nicely. And on the paper, you also can see this process is working. You can even see on the shiny part here is where it's printed on the glue itself, which flowed out a little bit over the paper. And the more darker areas are the paper itself. So if we zoom in using a SEM on the silicon on silicon samples, we can see that the film makes a very nice continuous path from the top to the bottom without showing any cracking or delamination anywhere. This tells us that there is no problem at the 90-degree edges and the corners because the particles apparently can stick to that very well. They have a very high conformity. You can even see the irregularities in the silicon surface. So for example, here you can see scratches made when we were cutting the wafer. And the particles actually filled those and are still showing those scratches. Here you can see a very minor crack, which is caused by um, there is some damage to the silicon here, and that apparently caused some stress. But at the 90-degree corner, it still works exactly as intended. On the bottom side, so this is where you have your polymer, the glue. We see the same effect. The transition from the silicon to the polymer is smooth, and we have exactly the type of coverage that we wanted. So the lines have a cross-sectional area of roughly 186 square micrometers, which is quite good. It's more or less the minimal size that we need. We don't want it to make it too thick because that will cause additional stresses. And you don't want to make them too thin because then your electrical performance is too low. So this is, I think, a fairly good compromise. This also makes sure that any surface morphology problems like hills or sharp corners can be crossed effectively. And the structure is highly porous, as you can see in the SEM image on the right. It's porous up to the nanoscale because the particles are somewhere between 5 and 20 nanometers. And that means that is also a problem for the electrical performance. If you can imagine, a bulk gold line has a conductivity of, I believe, 2.2 times 10 to the minus 6 ohm centimeters, which is roughly 35 times better than the lines that we've printed here, even though these are also pure gold. And this is most likely due to the porosity, because if you have not bulk gold, but a lot of essential air gaps inside your sample, this will reduce the performance, of course. It's uncertain if the process of printing on the side also has an effect. I don't know. It's not possible to characterize it as what the effect is of a 190-degree corner. But on a straight line, we have seen better performance than this. So I assume there is some increased resistance at the corners, but I'm not sure why that is yet. There is, however, more cracking if you have bad processing of the bonding polymer. So that itself can show a crack that will propagate through the nanoparticle film. So there's definitely some optimization needed to make a good bonding process. You can also see here where the polymer retracted a little bit and cracked itself at the silicon interface. This will, of course, create an open connection from the gold and completely destroy all performance. But this is not a problem of the printing technology, but of the die bonding technology. And the industry is much further with that than we are. So I'm assume we can fix this as well. So for silicon on paper, we see very similar behavior. So at the top edge, of course, it's identical to the silicon on silicon samples. So we see good conformity with successful crossing of the top 90-degree corner. And at the bottom, we also see a good transition from the glue to the paper. So this is all coated very uniformly with the gold nanoparticles. You can even see that the fibers themselves are coated with very high conformity of the particles. However, the resistance varied a lot more. And one reason for that is that it's difficult to measure the electrical performance on the paper itself. Because usually you measure this by having two needles that you put inside or on the electrode that you want to measure, and you force a current and measure the performance. But on the paper, placing the needles in such a way that you make a good contact with the nanoparticles is not easy, because you will either quickly scratch away the paper and the particles, or not, because it's so soft, not get a reliable contact. So what we then try to do is to probe only at the top. So write a U shape, probe from top to top, but this had some other drawbacks. So we quickly stopped doing that. But the interesting thing is, at least, that even the paper fibers themselves are coated conformally and everywhere on quite evenly. So even underneath other fibers and on these small flakes, it's all coated and still forms a conducting path, which is the important part here. Another problem we had is to try to bond the silicon to the paper. We used cyanoacrylate superglue, the most common type of superglue in the world, I think, which does make a very strong connection, but it also tended to crack a lot. So you see here that the polymer itself caused a crack here. And of course, this is terrible for your performance. So the yield of these samples was quite low. But once more, this is not a problem of the printing technology, but more of the method of making these samples. So that's an optimization step, but not a fundamental issue. So to conclude, it is possible to make these interconnects with a nearly unlimited step size. All you need to do is change the programming of the printer, and you can change how high you want to make your step. Film conformity is high. It follows every feature that you print on. And even a 90-degree corner is no issue. Conductivity is worse than bulk gold. Now, of course, this is annealed. This is not an annealed sample, which could improve it partially. And it's highly porous. So that can be a benefit, but also a problem, because you have lower conductivity. And it's completely dry at room temperature, so compatible with most materials. So the main challenges that we've so far seen is that it's difficult to fill the gap between the top and the bottom substrate. So for our next processing run, we would like to improve this. We have some ideas how to control this better and to isolate the surface to fill these gaps effectively. Another issue is that if you print on the side of your silicon, silicon is not isolated. That means that it is possible to make electrical connection to your silicon chip and not just the devices on top of it. This is not very difficult to stop. All you need to do is add an isolation layer on the side of the electronics. Then you can print safely on this. And one benefit that could have is that this can also make sure that the gap is filled properly and that there is no cracking, right? Because this isolation layer could also just function as a nice path to print on. The next thing we would like to do as well is to reduce the line width, because with the printer that we have right now and our options, smaller than 100 micrometers is not really possible. This is an engineering issue, so it's not something I'm focusing on. But in the field of microelectronics, where things quickly go to sub-micrometer size, or at least sub 10 micrometer. This is something that people ask me a lot if we can do it. And of course the processing speed. So it's possible for the wire bonding to make hundreds of, even thousands of connections in a minute. And here we use roughly 1 minute per line, excluding all the startup and mounting times. So it needs to be a lot faster, but if you have a very specific application where wire bonding is not possible, then this is of course not really an issue. So gold is a very nice material to use, but silver or copper would be cheaper. And especially copper is very popular because it's one of the best conductors thermally and electrically, widely available and cheap, but it oxidizes, and without any protective chemistry, this is almost impossible to print at the moment. But we want to test silver very soon. We also want to do more statistics on these lines and see if indeed the reliability is good, also after several months or many measurements. And we of course want to test it when we are bending the paper. Can the connection survive that? This has not been really extensively tested yet, because right now it's not possible to do a measurement when bending, but it should be possible in the future. And to make sure that this isolation problem is no longer there, and to prove that it can also work on different materials, we also print on non-conducting substrates like quartz and sapphire, and of course on polymers that are especially the ones used in microelectronics or lab on a chip applications. So that was about the work that I wanted to present here, and I would not have been able to do it without all the other people in my group. So I want to quickly highlight some of the people that are also working with this printer in our group. So there's a team working on gas sensors using nanoparticles as a functional layer in a gas sensing device. So Leandro Sacco, Donghu, and master student Esat Beitli. And die attach materials, so trying to connect chips to a surface reliably in a way that it's either conducting or thermally conducting, where I'm working on it with my colleagues Shinrei and Dong. There's also a small section in our group that collaborates with the bioelectronics group. So that's PhD students Nassim and Hande, who make lab on a chip devices or implantable neurostimulation devices. So with that, I would like to end my presentation. So if anybody has any questions or is interested in working with this technology with us, don't hesitate to contact me or reach out to me in any way. Thank you for listening.
Thank you so much, Joost. I hope our audience found this interesting. I would like to give our audience a moment to ask questions. Either raise your hand so you can be unmuted and you ask the questions directly, or please write it in the chat if it's more comfortable for you this way. And I see we have our first question. Pauline Sandaria. Can you unmute Pauline so she's able to ask her question?
Yes, Pauline, you are unmuted. You can just unmute yourself and ask the question.
Yes, thanks. Hi, Joost. Thanks for the presentation. Really liked it. I was wondering if you already presented the work at a conference, or that you had some feedback from specialists in the researchers or industry that actually work on these interconnects, and what their feedback was on the work you did.
Yeah, so I presented this at the EMPC conference that was online in Göteborg last month. And their main questions were where would you apply this? So, of course, paper and soft materials is one, but they also felt that it would be interesting to try and use it on very hard materials, so like silicon carbide. And they were thinking that if you, so silicon carbide is so hard that it's not possible to drill a hole through it, or not easy at least. And that means that if you want to connect the front to the back of the chip, it is not possible unless you go around it. And to shorten the pathway, you want to print on the side of the chip, and that could be one application of this. They were also thinking of power electronics. I'm not so sure if these lines are suitable for high power connections. But all in all, they were quite interested in it.
Okay. And are there still some, so you talked about the conductivity being like worse than the gold, but is it sufficient for these type of applications?
Yeah,
That's still an issue, or?
it is. So in the end, conductivity just means that if you have a high resistance in your wires, you need more power to drive a signal, or that you need shorter pathways because your signal is getting weaker the longer your path is. So unless you make very long connections, I don't think this is really an issue.
All right, thanks. Thanks.
Thanks.
We also have a question in the chat. You mentioned that there is a 34-fold reduction in conductivity before annealing. Have you tried annealing? I hope I pronounced this all right. The sample?
Yeah, so it's an annealing actually, but
Annealing, I'm sorry.
we haven't done it on these samples, but we have done it on flat gold lines. So there we printed them on silicon with electrodes to probe them. And after annealing at, I think, 200 degrees, we had a conductivity that was only 7 times worse than bulk gold. So then you're already fairly close to what is possible, I think, without completely melting it. And that could be applied here too. You could put it in an oven. I'm not really sure if the heat will cause stress that will cause cracking, which is one reason why we haven't tested it yet, but it's certainly something we want to do. But also, I think that if you want to use this for fragile materials, I think the nice thing is if you can make this work without annealing, because then you don't need the heat to that can damage, for example, your devices. Hope that answers the question.
Thank you so much. Last shout out. We have another question. Do you have adhesion problems with the printed gold? Do you apply a protective coating after printing?
Well, the adhesion of the gold to silicon oxide is known to be very bad. In industry, they use a thin layer of chrome as adhesive layer. But it's not possible to do that here because you would need to print unoxidized chrome and then gold, which is not, at least not possible with our setup. But in general, because they are only stuck there with van der Waals forces, it is easy to wipe them off by a tweezer or by a tissue. So in that sense, yes, it would be good to package them. And what you usually see in chips like this is that they are typically packaged in epoxy resins. So then everything is immobilized, and you could also coat it with a thin film of some insulating material to fix everything. But in general, if you don't do anything with it, it will stay as it is right now. So Delamination only happens if you treat it with something.
Thank you so much, Joost. And this was our last question. Our time is up. I would like, first of all, to thank Joost for co-hosting this session and for his topic today, which I hope was interesting and thought-provoking, not only for us, but also for our audience. I would also like to thank our audience for being here with us, and I hope to see Joost in our future webinar endeavors. So thank you so much.